from those small perturbations in the early universe, those perturbations grow. And those perturbations led to the formation of structure. And from the formation of structure, you form galaxies. And from the formation of galaxies, you form stars, planets, and so on. And you form us.
Hello everyone! Welcome to liknayan.podcast, and ako si Cherry.
Ako si Philip.
And for today, we have a new guest. We have Tram Acuña from Taiwan para mag-share ng kanyang research with us. So welcome, Tram.
Hello.
Please introduce yourself.
Hello. Okay. So, ako si Tram. Right? So, currently, postdoc ako dito sa National Tsinghua University sa Hsinchu. So, mostly yung research focus ko ay astroparticle phenomenology. So, previously nasa Italy ako. I did my PhD in SISSA and I focused on dark matter physics. And then, nung lumipat ako dito, medyo nag-shift yung focus ko towards primordial black holes and stochastic gravitational waves and pulsar timing. So, at least yung pulsar timing na discuss na ni Reggie sa previous episodes.
May overlap pala kayo ni Reggie, no? Sa ginagawa.
May konting overlap. Although, yung pulsar timing sa trabaho namin, so we use it in a different way. So, we use pulsar timing para i-probe yung primordial black holes. Right? So, medyo iba siya sa gustong, or at least sa research efforts ni Reggie.
Wait, so pag sinabi mong primordial black holes, parang yun yung sa mga early start ng universe, mga Big Bang, mga ganun.
Exactly. So, yung primordial black holes na to, iba ito sa astrophysical black holes na alam natin at na-observe, diba? So, recently, anong year ba yun na-award ng Nobel Prize yung observation ng black holes? Or was it given the Nobel Prize?
Ayun, kailan ba yun? Hindi ko na maalala.
Yung Event Horizon Telescope. So, at least, alam natin meron tayong image ng black hole from the Event Horizon Telescope. So, at least we know that black holes exist and we know yung origin nila, right? So, galing siya sa collapse ng stars. Pero itong primordial black holes na to are quite different kasi from the name itself, primordial, they are, at least so, hypothetical lang to, so wala pa tayong nakikitang primordial black holes. Although, they're proposed to be produced in the early stages of the universe. So, sabi nga ni Philip, around the Big Bang. Around the Big Bang nucleosynthesis, around that time.
Iba-iba palang klase yung mga black hole.
Pero may common feature sila eh. Kasi itong primordial black holes na to, they are, so usually yung mechanism ng production nila ay galing sa collapse ng overdensities, right? So, when gravity wins over, we have a runaway process, magko-collapse ka into a black hole. Pero mayroong critical density, right? And alam natin, in the early universe, right, sabi nga doon sa kanta ng Big Bang, di ba? The universe started in a hot, dense state. So, kailangan natin, so, the conditions are perfect yung conditions sa early universe para ma-produce yung primordial black holes. Right?
Well,
is there a way to observe black holes? I mean primordial black holes.
That's a very good question. So, yun yung in-address namin sa recent paper namin nung PI ko. Right? So, kaya pumapasok dito yung pulsar timing. Okay. So, alam natin that pulsars emit regular electromagnetic signals. Right? So, para silang lighthouse sa universe, diba? So, space, right? And in-exploit namin, so we can exploit yung regularity ng signal na yun. So, kapag meron kang compact object, so it could be primordial black holes, it could be anything, right? Once it passes close to a pulsar, right? So, pwedeng mag-impart ng velocity doon sa pulsar, right? So, gagalaw ng konti yung pulsar. So, parang meron kang analog ng Doppler shift doon sa electromagnetic emission. Right? So, kung alam mo na regular yung signal, tapos nakita mo, merong Doppler shift, pwede mong i-back-calculate yun. Right? So, if you interpret that change in signal, right, as induced by the passage of a primordial black hole, pwede mo ngayong infer ano yung properties ng primordial black hole na yun, ano yung mass, gaano karami yung dumaan. Right?
So, halimbawa, if you're able to observe primordial black holes, tapos ngayon naka-observe din tayo ng black holes, may time-dependent properties, so to speak, ang black hole, like iba yung properties ng black hole na na-observe ngayon sa this time, around this time, and then yung time na early beginnings of the universe, and so on. So, halimbawa, let's say, 13 million years ago, ito yung klase ng black hole na meron. And then, 8 million years ago, ito yung klase ng black hole. And then, 1 million year ago, ganito. So, may possible ba na malaman, ma-distinguish kung anong time siya na form?
Okay. So, I think yung gustong patungan ni Cherry yung merger history ng black holes, right? So it's something na hindi namin inapanton sa study namin. So, sabihin na natin, it's a limitation of the study. So, hindi namin tingnan yung merger history. Inassume lang namin na, na-produce sila in the early universe, and then yung abundance sila is in such a way na conserve yung number nila from the time of production until now. And then ignore namin yung possibility na mag-merge sila, right? Kasi ang black holes pwede sila mag-merge. Pag nag-merge sila, pwedeng lumaki yung mass nila, they can grow, right? Pero it is something na in-ignore namin sa analysis namin. So we just said, if we produce black holes of, let's say, 10 to the minus 8 solar masses, right? Kung gaano sila karami, nung na-produce sila, ganun din sila karami at present time. And yung abundance nila sa local galaxy ay more or less a fraction of the amount of dark matter in the halo. So, maraming assumptions na pumasok doon sa analysis.
Okay.
Right? So, but that's a valid question. Right? So, if you want to be more realistic, syempre kailangan mong i-account yan. Right? Pero yung goal lang ng study namin is to assess kung kaya ba ng future generation pulsar timing facilities like the Square Kilometer Array na ma-probe itong primordial black holes na ito.
So, ang dami pala ng mga magkakaibang ginawa mo, Tram, no? May ano nga ulit yung ginawa mo nung undergrad? Iba pa yun, di ba? Undergrad. Tapos
ano yan, gravitational physics naman yan.
So gravitational physics, tapos napunta ka sa mga primordial black holes, dark matter. Tapos ngayon, ano na siya, di ba? Yung high energy mo mga astroparticle physics.
But I would say na yung academic journey ko started with gravitational physics. Then, nung nasa Trieste ako, I moved to dark matter phenomenology and particle phenomenology. Right? And then, nung lumipat ako dito, doon na nagsimula yung primordial black holes study and pulsar timing and first order phase transitions. So, yan.
So, may weird question ako kasi para na-mention na you're doing high energy astrophysics. Bakit siya termed na high energy? Is there a low energy na astrophysics field din?
Okay, so first of all, how do I explain this? Kasi medyo malawak yung field ng high energy astrophysics right? So, let's say when you consider systems where you have creating objects around the black hole, right? So, black hole, it sucks everything, right? And then black holes can accelerate objects at very high speeds, right? So, in that sense, right? Kung pag-aaralan mo yung mga ganang klaseng system, right? So, siyempre, papasok na doon yung element ng pagiging high energy ng system. And then, halimbawa na lang, right? Yung pwede ka mag-produce ng high energy particles in that process, right? In the form of luminous jets from these black holes. Merong mga astrophysical objects, ang tawag sa kanila, active galactic nuclei. Right? So, these are strong emitters of X-rays. Right? And yung mechanism ng pag-produce nun is mostly from synchrotron radiation. Right? Although, yung klase ng high energy stuff na ginagawa ko, it's not really related to those things, right? So, I would say that I am more of a particle cosmologist. So, at least yung training ko is Astroparticle Physics. Pero I would say it's more appropriate to label me as a particle cosmologist.
So, anong pinagkaiba nun sa, for example, sa mga ginagawa ng mga tao sa CERN? Kasi di ba particle physics din yun?
I see.
So, bakit sila, yung ginagawa nila doon sa particle physics is titingnan yung collision ng mga particles doon sa Large Hadron Collider. So, anong pinagkaiba ng mga ginagawa ng astroparticle physicist sa kanila? Bakit yung sa inyo, bakit yung sa space yung tinitingnan nila?
Right. So, that's a very good question. So, yung mga nagtatrabaho sa CERN or those people who are doing LHC physics, katulad ni Marvin Flores, right? So, you can more or less label them as collider physicists, right? So, you know that colliders, mga malaking machines to that can smash together particles at very high energies at very high speeds, right? And of course, pwede mong itanong, bakit natin kailangan ng colliders, ba't natin kailangan pumunta sa high energy? Kasi gusto natin makita kung kaya ba natin mag-produce ng new particles, heavier particles, and so on. And to do that, you need high energies. On the other hand, if, say, you're doing astroparticle physics, ibang klase you're still looking at high energy particles, pero iba yung origin nila. So, obviously, yung origin nila are astrophysical, or it could be that they also come from the early universe. So, yung perfect example dyan, yung tinatawag ng cosmic microwave background. Right? So, yun yung leftover heat from the Big Bang. So, these are cosmic photons na nanggaling sa Big Bang.
So magkakaiba yung mga particles na napoproduce, for example, pag nag-collide siya, at yung mga particles na napoproduce doon sa mga black holes na nabanggit mo kanina.
I wouldn't say they're different. We're still talking about the standard model. Parehas sa particles pa rin yan.
Okay.
Pero iba lang yung origin, iba lang yung production mechanism. Right? And may mga astrophysical systems that are actually much more powerful than the LHC, let's say, at kaya nila makapag-produce ng particles at much more higher energies. Right? So ano ba yung energy reach ng LHC? 10 TeV, right? Well, in principle, you can produce particles that are much more energetic than that, right? At least...
so, bali parang yung pagtingin sa mga sa space ng mga astroparticle physicists ay para ma-probe yung energy scales na hindi kayang matingnan sa sa LHC.
You can put it...
Tama ba pagkaintindi ko?
May that's one way, right? Pwede mong isipin na complementary yan sila, right? So, let's say you want to find supersymmetry, you want to find supersymmetric particles, right? So, we try as many ways as we can to look for these particles. So, merong collider search, or you can look for signals in astrophysical systems. So, halimbawa, kung meron kang anomalous na signal, like let's say a cosmic ray signal, right? pwede mong interpret yun as some signal of the annihilation of new particles like dark matter particles.
So, di ba sa Astroparticle Physics, madaming dyan, may dark matter, may dark energy, may mga black holes, may mga gravitational waves, may mga cosmic microwave background, may mga pulsars.
Yes.
So sa mga lahat ng mga celestial objects na yan na involved sa astroparticle physics, ano yung parang sa tingin mo yung pinaka-interesting para sa iyo? Ano yung implications nito para sa understanding natin sa universe? Yung pag-aaral ng specific celestial object na yan.
Okay. I wouldn't call it a celestial object, pero I would say na siguro yung pinaka-importanting discovery is na related sa astroparticle physics, yung measurement ng cosmic microwave background. At yung measurement ng anisotropy ng cosmic microwave background. Right? So, medyo maabang story ito, no? So,
so sige, take your time. Paliwanag mo yung cosmic microwave background.
So,
at ano yung ibig sabihin ng anisotropy?
Okay, sige. So, unahin mo natin yung cosmic microwave background. So, again, yung prediction ng Big Bang cosmology, right, is the presence of these leftover photons from the Big Bang, right? At yung prediction na yun, ang sinasabi, yung temperature ng photons na yun is at 3 Kelvin, right? And kung ita-translate mo yun into some wavelength, right, assuming na black body yung distribution ng photons na yun, it would be somewhere in the microwave band. Kaya siya tinawag na cosmic microwave background.
Okay.
So, ngayon, paano mo siya mahanap? Right? So, noong 1967, merong dalawang physicists na nagtatrabaho sa Bell Labs, si Penzias at si Wilson. Right? So, meron silang na-measure na signal, hindi na kung saan galing. Isip nila, galing ba ito sa mga military installation or galing ba ito sa aliens? Right? Tapos may time na nakita nila, merong mga special white stuff doon sa receiver dish nila na galing sa mga ibon. Right? Pero eventually, they pinned it down to the leftover heat from the Big Bang. Yung sinasabi ko kaninang 3 Kelvin. And then, because of that discovery, nanalo siya ng Nobel Prize. And that is definite evidence that the Big Bang happened. Right? And yung isa pa, right? So other than yung black body distribution, nakita nila na isotropic. So ibig sabihin, kahit saan ka tumingin sa sky, pare-pares yung signal na makikita mo ng cosmic microwave background. Pare-pares yung temperature na mami-measure mo. Right?
Bali parang constant siya, yan yung ibig sabihin.
Constant in every direction. Saan ka tumingin sa sky, right? Siyempre, kailangan mong isubtract yung kung ano mang background, kung ano mang foreground, ganyan. Pag sinubtract mo lahat yun, makikita mo uniform. Actually, kung meron kayong television set sa bahay, right? Tapos kung meron pa ba ng mga TV na may mga antena?
Wala na.
Yung mga CIT na
babalikan na
TV.
lang natin yung childhood natin. Diba? Ganyan ba ng antena yun sa labas?
Yung ayusin mo pa, diba? Tapos, well, kung fortunate kayo na meron pa kayong ganong television set sa bahay, tapos meron kayong makita static doon, part ng signal na nakikita nyo sa screen ay galing sa cosmic microwave background, galing sa Big Bang.
So, ibig sabihin pala, lahat kami nagkaroon na ng chance na makakita ng cosmic microwave background.
Well, yeah. Lahat tayo. Kung nakita kayo ng static na sa TV.
At least tanda ng mga millennials. Wala na yung mga Gen Z.
Wala na. Na-observe pa natin ng fragment ng Big Bang. It's such a millennial brag.
Yes, exactly.
So 3 Kelvin, 3 Kelvin yung temperature ng cosmic microwave background, tama ba?
Yung present temperature.
Yung present.
No photons.
So ibig sabihin, lumalamig
So, over
dapat
time,
siya.
bababa pa siya.
Yes, kasi nag-expand yung universe.
So, at the time of Big Bang, ano talaga nun? Temperature talaga nun?
Sobrang laki. Okay. Pero it depends.
Okay.
It depends sa question, right? So, depende kung ang question ay at the time of production of these cosmic photons, right? Ano yung temperature ng photons na yun, right? So, kung yung time of last scattering, alam ko kasi temperature in electron volts So, 0.2 EV. Ano siya in Kelvin? Di ba? Ano yan? Naalala ko yun sa lecture ni sino ba yung condensed matter? Sino ba yung semicon?
Si Doc Salvador.
Lagi niya sinasabi sa amin noon. 25 MeV, immediate electron volts is 300 Kelvin. So, yan. Convert na lang. 0.2 EV.
So, 300 ano yan?
300 Kelvin. 300 Kelvin is 25 million electron volts. Right? So, yan na lang.
Convert na lang.
Exercise for the student.
We leave it to our viewers to convert. Pero it also
Maglagay tayo
means...
ng calculation dyan.
It also means, diba, na habang tumatagal pa, bababa pa yung 3 Kelvin na yun na current temperature.
Oh, yes.
So what happens when it reaches 0 Kelvin?
It cannot reach 0. I mean, at least...
it will only approach 0.
But
never reach 0.
Never reach 0. Pero diba, sa... Ano ba yun? Second law, third law of thermodynamics, diba? You can't reach exactly 0, diba?
So, bali in essence, yung cosmic microwave background ay proof na nangyari yung Big Bang. Dahil na-detect natin siya as evidence.
It's just one evidence.
Okay.
So,
bali parang...
marami pang evidences. Halimbawa, yung abundances nung primordial abundances ng light nuclei. So, yung hydrogen, helium, right? Of course, babalik tayo sa question, what are we made of? Diba? So, syempre, yung sagot dyan, we're made of stardust, which is entirely true. We're made of stardust. Kasi yung heavier nuclei are produced in the stars. Whereas yung light nuclei, they're produced in the early universe, hydrogen, helium, and then at the time of star formation, so syempre magko-collapse sila, right? And then through some star formation mechanism, pwede ka mag-produce ng heavier nuclei. I-produce carbon, oxygen, nitrogen, all those things. And then pag may supernova explosion, syempre lahat ng material na yon, it will just fly out. Yun yung stardust, diba? So, but in any case, yung primordial abundances ng light nuclei is another prediction of Big Bang cosmology, and it is something that we have measured and matched yung prediction ng Big Bang sa measurement, sa observation.
Okay, so bali, meron tayong cosmic microwave background, tapos yung abundance ng hydrogen and helium atoms, which are evidences ng Big Bang.
Yes.
So, di ba may bagong discovery ngayon, which is yung nanohertz na gravitational waves? Masasabi mo ba siyang kasama siya sa mga evidences na nangyari nga yung Big Bang?
That's a good point. So, at least yung discovery ng nanohertz gravitational waves, as mentioned by Reggie before sa mga previous episodes, it's just evidence na meron kang source of stochastic gravitational waves sa universe.
Okay, meaning, ano yung meaning ng stochastic?
Stochastic. So, the thing is, yung stochastic niya, hindi natin alam kung ano yung exact origin. Di ba? So, may mga proposals. Pwede siyang galing sa merger ng supermassive black holes or pwedeng galing siya sa first order phase transition sa early universe.
Okay.
So, at least yung isa sa mga inaaral ko ngayon is yung first order phase transitions. Right? So, generic prediction ng first order phase transitions. First order phase transitions, yung production ng gravitational waves. And to some extent, yung observation ng nanograph can be explained by this. Pero hindi pa natin mapinpoint ito ba talaga kasi ang daming alternatives eh. Right? They can all explain the same signal. So, meron kang degeneracy. Question is, how do you break that degeneracy? How do you rule out one? And how do you say na ito talaga yung production mechanism?
Pero di ba in essence, parang kung iisipin mo, parang yung nanohertz gravitational waves, parang counterpart siya ng cosmic microwave background na ano. Parang nasa background lang siya ng buong universe. So parang bakit, for example, sa cosmic microwave background, wala bang parang mga ganong problems din dati on how to parang mga ma-eliminate yung mga other explanations? Diba? Kasi during that time, well, mas advanced yung technology natin ngayon, diba? Pero bakit yung parang pag-rule out ng mga other explanations, mas mahirap ba siya gawin ngayon?
So, balik tayo so, let me address yung question, okay? So, yung case ng cosmic microwave background, hindi ako sigurado kung merong alternatives doon sa pag-explain nung 3 Kelvin na signal na yun. I think if you look back in history, it's more like maraming proposals on what the origin of the universe is. Ano ba yung tamang cosmological model? Kasi dati, merong proposal si Fred Hoyle na yung universe natin is steady-state cosmology. That it is eternal, it is not expanding, it has stayed the same from the beginning up to now. Problema dun sa model na yon, kailangan nilang magkaroon ng kailangan i-introduce yung notion na mass cannot be conserved. Right?
Okay.
Whereas yung Big Bang cosmology, okay, yung idea is you have an expanding universe. Problem, walang prediction. Right? So, of course, yung prediction, it was worked out na meron kang leftover heat from these cosmological photons. Nung na-measure yon, that rolled out yung steady-state theory ni Fred Hoyle. Right? Now, taking that analogy doon sa stochastic gravitational waves, I think wala pa tayo ata sa sensitivity na kaya na-roll out yung different possibilities na yon. So, at least for now, we are still unsure of the origin, or at least let's just say na this is an exciting time to study stochastic gravitational waves. Both from a theoretical perspective and also from an experimental point of view.
Speaking from an experimental point of view na sinasabi, syempre nang alam ko. So, how close are we? How close are we to observing these kinds of phenomenon in the universe? Yung level of technology ba natin kaya na? Or kulang pa?
It's a very broad question, right? So, depende kung ano yung gusto mong sukatin, diba? So, kung babalik tayo dun sa cosmic microwave background, right? So, since 1967, yung prevailing notion was that yung cosmic microwave background, uniform siya. Right? All throughout, in any direction. Pero that also signals some sort of a problem. Kung uniform yan, paano ka magkakaroon ng overdensities? How do you produce structure in the universe? How do you produce stars? How do you produce us? Kung isotropic lahat, right? Walang perturbations, we won't be here. Right? So, may suspicion yung mga tao noon na it could be na yung cosmic microwave background hindi talaga siya homogeneous isotropic. Well, not homogeneous, not isotropic at all. Right? So, people have worked out, okay, what if you introduce perturbations, right? And there has been a long history of study on this, right? Kaya nanalo si Peebles nung Nobel Prize because of his work. Peebles. James Peebles.
Okay. Peebles?
Peebles. So, nanalo siya ng Nobel Prize recently because of his work on cosmology. And part ng trabaho niya is on working out, right? Ano yung level ng anisotropies na makikita natin sa cosmic microwave background, right? So just to give you an idea, ano yung level of anisotropy, it's around 1 part in 10,000. Right?
So sobrang liit lang.
Sobrang liit nung anisotropies na makikita mo dun sa temperature ng cosmic microwave background. And at the time of Peebles and other cosmologists in the 70s and 80s, syempre wala pa sila doon sa level ng technology na yan. Okay. Now, if you talk with Americans, sabihin nila, okay, yung first na attempt to measure the anisotropy was COBE, C-O-B-E, Cosmic Background Explorer. Right? But prior to that, yung mga Russians, they were also aware of this. So, sila nag-launch din sila ng project nila, which is called Relic 1. Yung goal nun, again, is to measure the anisotropy. They had the technology back then.
Pero yung 1970s? Tama ba?
I'm not sure kung kailan exactly na work out yung level ng anisotropies, but I'm certain that in the mid-80s, meron ng proposal yung mga Russians to send a satellite in space to measure the anisotropy of the cosmic microwave background. Yung COBE, which was an effort by the Americans, was launched around early 90s.
Okay. So, mali parang yung anisotropy na yun, na maliit, yun yung parang yun yung masasabi mong cause kung bakit nandito tayong lahat?
I would say so. Yes. Part of it. It's part of the story. It's also part of... Sorry.
We are here because of very, very tiny perturbation in the universe. Tama?
Pero kasi, yes, that's true. Pero those perturbations actually grow during the expansion of the universe. If you actually work out, right? Ano na yan? Perturbation theory ng Einstein field equations yan.
Okay.
So, you start with linearized Einstein field equations, work out mo yung evolution ng perturbations. Of course, pag nasa non-linear regime ka na, hindi mo na pwedeng gamitin yung linear theory.
Hindi na pwede.
Pero yung point is, from those small perturbations in the early universe, those perturbations grow. And those perturbations led to the formation of structure. And from the formation of structure, you form galaxies. And from the formation of galaxies, you form stars, planets, and so on. And you form us.
Masyadong existential na.
But it's just so remarkable na there are things that we can... We started with just a very set of assumptions. We can actually work out consequences that are far-reaching, that actually, go into questions of how did we came to be, ganon, di ba? Paano tayo nag-exist? Yan. which is quite interesting. I would say.
Pero it all started with just a prediction, right?
Yeah. Or at least some idea na kailangan mo kang perturbations.
So, halimbawa, balikan pa lang yung minention mo kanina with the observation of the cosmic microwave background. So, di ba nagpadala sila ng satellite?
Yes.
So, paano mo malalaman where to go? Paano mo mapipinpoint na, siguro around this area, baka may ma-observe tayo na anisotropy or something?
Well, so medyo leaning na yan sa observational cosmology side. So, hindi ako masyadong expert on this, right? But what I do know is from standard cosmological model, alam natin na the universe is homogeneous isotropic at large scales, right? So it doesn't really matter kung saan ka titingin, right? Yung important lang, syempre, you just send your satellite to space. Right? Siguro, I guess, eliminate background, right? And other stuff, right? But of course, pwede rin naman mag-measure ng cosmic microwave background sa Earth, right? But yeah, of course, it's better if you do it in space. And also, may mga subtraction ka pang kailangan gawin, right? Kasi yung solar system natin is moving around the center of the galaxy at a speed of around 200 kilometers per second. Right? So, kailangan mo pang isubtract yung part na yun. Otherwise, may makita kang dipole structure ng CMB. I'm not sure kung yun yung origin ng dipole structure ng CMB. But the point is, if you're moving relative to the CMB, may makita kang dipole structure. May parts ng CMB that would be redshifted. May parts ng CMB na makita mo blue shifted. Right?
Okay.
So, kung gusto mo makita yung hindi yung unshifted form ng CMB, kailangan mong isubtract yung velocity natin relative to the CMB.
Okay. Pero gusto kong balikan pala yung point kanina na, di ba, magpapadala ng satellite. Tapos yung satellite na yun, gagawa siya ng measurement. Tapos yung ginagawa niyang measurement is a send a signal sa Earth. Eh di sobrang tagal pala ng ganyang type na experiment. Kasi di ba, sa interstellar, di ba, para may imagine for example ng viewers at natin. Di ba sa interstellar, may sinulit yung actor doon, basta pinadala nila sa space, tapos every time na mag-video call, ilang taon bago ma-receive ng mga tao sa Earth yung video call niya, tapos yung reply, ilang taon din. So yung mga ganyan type pala na experiment or mga observational na mga ginagawa, edi aabot yun ng mga ilang decades.
It's more like, let me put it this way. Kasi maraming missions na pinadala para i-measure yung cosmic microwave background. So hindi lang Kobe, meron Planck experiment or Planck satellite. Effort siya ng European Space Agency. So yung main goal niya ay para sukatin yung anisotropy ng cosmic microwave background to a better precision level compared sa Kobe. Kasi yung Kobe meron siyang measurement pero hindi ganun ka-precise, right? And then when Planck came, mas precise na yung measurement sila nung anisotropy, right? So I would say matagal yung time span, right? Para ma-infer ano yung actual level of anisotropies. And it's mainly because of technological issues.
Okay.
Kasi yun nga, so balik tayo doon sa question ni Cherry kanina, right? Nandun na ba tayo sa level ng technological expertise in such a way na ma-measure natin yung anisotropy? And the answer is yes, right? But of course, syempre, depende ano yung gusto mong level of precision, right? Okay. And syempre, maraming data releases yan kasi kailangan nilang aralin ano ba yung foregrounds, ano yung backgrounds. Kasi hindi lang naman cosmic microwave background yung makikita mo sa outer space. Marami ka pang source of photons. Marami kang source ng noise. So, those parts are actually separate fields of themselves. Malawak na field of study yan. May mga PhD students na yun lang yung ginagawa nila, paano mag-subtract ng error, paano mag-subtract ng noise.
Sobrang hirap pala na problem.
Kasi hindi siya non-trivial issue yan. Right?
So siguro to wrap up at looking ahead. Kasi madami ka namang nabanggit na maraming mga space missions, ganun. So looking into the future, ano sa tingin mo yung mga magiging promising developments ng field bukod doon sa cosmic microwave background na anisotropy?
Sagutin ko na lang yung part about unanswered questions. Right? So still, I think yung isa sa mga pinakamalaking unanswered questions, at least sa cosmology, is yung nature of dark matter. Right?
Okay.
Kasi alam natin dark matter exists, right?
Wait lang, bago pala yan. So, bakit dark matter yung tawag? Tapos, ano yung dark matter?
Okay, sige. So,
why is dark matter dark?
Why is
tapos, bakit siya important? Yan.
So, I guess kailangan natin ng additional na episode on this, pero just to shorten my answer, right? So, dark siya kasi it doesn't interact with photons or with normal matter, but we know its existence kasi it exerts gravitational influence, right? So, it can alter the motions of objects, yan. So, yung typical na explanation or this typical na evidence for dark matter is yung galaxy rotation curves. That as you go farther and farther away from the galactic center, makita mo yung circular velocity constant pa rin instead of going down according to Newtonian prediction. Okay. So, it's one evidence that dark matter exists, and it is some kind of matter kasi alam natin pressureless siya. So, yung equation of state niya is such that yung pressure is zero. Right? And we know the amount of dark matter in the universe precisely because of the CMB. So, babalik lang tayo sa CMB.
Okay.
So, yung level
Napakarami palang malalaman from CMB.
Exactly. Kaya I would say na yung cosmic microwave background, isa sa mga pinaka-importanteng discovery sa cosmology.
Okay.
Galing.
Yeah. So, dark matter siya kasi parang technically hindi natin siya nakikita dahil hindi siya nag-inspire.
And
ordinary
matter.
For example, nakikita natin yung color red dahil for example yung bola na to, once na matawaan siya ng light, i-absorb niya yung lahat ng wavelength except sa red, tapos yung red yung magre-reflect. Yan yung nakikita natin na red. So sa dark matter naman, parang ino-absorb niya lahat or hindi talaga i-interact yung light.
Tatagos lang siya. Wala, dadaan lang.
So wala talagang zero interaction talaga, as if wala siya doon.
Well, so far wala pa tayong nakitang interaction, but then somehow again you can branch off from there and start a new field, and it's actually something na ginawa ko ng PhD. Well, it's an effort that spans several decades, which is to find whether or not dark matter has interactions with normal matter, right? So far, wala pa tayong nakita. So, you can say it's zero, but somehow we hope that it's non-zero.
Tapos madaming theory na ginawa. Para sa efforts na hindi siya zero.
Maraming models. So, part din ng PhD ko is, yun, propose a model for dark matter.
Bakit important yung dark matter?
Well, important siya kasi, again, alam natin sa cosmic microwave background that to explain yung anisotropy, you need some amount of dark matter, right? So, if, kung hindi mo, well, It's just a natural question. Ano ba talaga yung nature ng dark matter? What is it made of? Of course, we know what dark matter is not. Alam natin na wala siya standard model. It's not ordinary matter. It has gravitational influence. It has little to no self-interactions. Yun lang. So ano siya?
So in essence, pwede siya dapat, kasi naalala ko, nabanggit din to ni Reggie dati. So ngayon, pwede na dapat siyang ma-detect or expect natin na pwede siyang ma-detect gamit yung gravitational waves.
It really
Kasi
depends
may
what
gravitational interactions.
But it also it also begs the question, ano yung ibig mong sabihin ng detect, right? Kasi kung ang tanong ay kaya ba natin ma-detect yung influence on dark matter, the answer is yes. After all, yun yung evidence natin for dark matter, yung gravitational interaction. Pero kung yung tanong ay ano yung composition ng dark matter, ano siya? Is it a fluid? Is it a particle? Are those aliens? Ay, biro lang. Okay. Yung tanong na yun, it's still, well, it's one of the holy grail questions in physics.
Actually. Pero kailan nag-start yung idea ng dark matter?
Mabang story yan. Several decades ago. Kaya kay Fritz Zwicky, ano siya, Austrian na astrophysicist. So, actually, ang ginawa niya, meron siya observation ng stars. Measure niya yung velocity ng stars in this galaxy cluster. And nakita niya, why are they moving faster than they should be? Right? Kasi, so, galing doon sa amount of light, galing doon sa galaxy cluster na yon, kaya mo masukat gaano kabigat yung galaxy cluster. And from there, kaya mo ma-infer ano yung average velocity ng mga moving objects dun sa cluster na yun. Right? And he found out na they're moving faster than they should be. So, ang natural na inference, there must be more matter inside that galaxy cluster. Right? Pero hindi niya
yung dark matter.
Hindi niya ma-account yun based on observations. Hindi niya ma-account yun based on the light that we observe. So, kaya niya sinabi na, maybe there's some dark stuff inside. Of course, syempre, pwede mong sabihin, baka they just emit in the infrared or they just emit in a different wavelength. So, it turns out na kahit na tumingin ka doon, right, hindi ko yung ma-account yung total mass doon sa galaxy. It's just a term that we use as a placeholder for something that we don't understand.
So siguro to wrap up, parang di ba sa discussion natin, parang sobrang bigat niya na field na aralin.
Yes.
So ano yung advice mo, Tram, para sa mga estudyante na gustong mag-aaral sa field na to? Kasi pag papakinggan mo yung explanation at lahat-lahat, parang sobrang dami mong kailangan aralin na math, physics,
nakaka-overwhelm.
Lahat ng mga bagay. Nakaka-overwhelm na siyang pakinggan. So ano yung mabibigay mong advice?
I mean, I would say seryosohin yung pag-aaral ng physics. So kasi, halimbawa, if you work on cosmology, right, maraming physics na involved. Right? So, hindi lang relativity, kailangan may knowledge ka rin, may solid background ka rin sa quantum mechanics, astrophysical physics, and other fields in physics. Pangalawa siguro, discipline and focus. Right? I think it applies naman kahit anong field. And also perseverance. Yung importance ng hard work. Yan. Pero tingin ko rin importante yung meron kang tawag dito, role models, right? Meron kang support group,
Okay.
Kasi in general, when you study physics or at least when you do research, it can be a lonely journey. Diba?
Yes.
Importante yung meron kang nakausap. And
Ka-brainstorm.
exactly. And what else? Well, try to talk with experts. Ganun. Huwag mahiya. Diba? You can ask any stupid question. Naalala ko yung sabi nung quantum field theory professor namin, there are no stupid questions, only stupid answers.
That's true.
Importante na lagi magtanong. Right?
Pero for example, mga libro, ano sa tingin yung ma-advise mo na magandang libro na aralin ng mga beginners?
Marami. Depende. So, kung cosmology, sabihin natin Dodelson. So, yun yung isa sa mga basic textbooks na pwede nang simulan. Actually, I would say these days, marami ng lecture notes na available online. So, we're not just limited sa mga libro. Kung gusto nyo mag-aral ng cosmology, pwede nyo tingnan yung lecture notes ni Daniel Bauman. May introductory lecture notes siya on cosmology. At least yung starting level is at least yung background. Kailangan meron alam sa general relativity, quantum mechanics, and particle physics, and statistical physics. Right? So, siguro, kaya matapos yung...
Ako siguro yung madadagdag ko lang din. Kasi yung daming physics ng mga yan. So, kung for example, sa mga gustong mag-take ng physics sa college, seryosohin na lang muna yung algebra nila at calculus. Kasi yun yung foundation ng lahat. Dapat may strong grasp ng basics ng algebra at ng calculus kasi yun yung foundation ng lahat ng physics.
I think in any branch of physics naman. Naalala ko nung before ako pumasok ng NIP, sinabi sa akin na math is the language of physics. So, kung hindi mo kaya magsalita, mahirapan ka.
But again, yun yung technical aspects. Diba? I mean, kailangan alam mo yung basics. Pero yung isa pang aspect is stay curious and stay inquisitive. Yan. And try to see the big picture. Minsan kailangan mo tanongin yung sarili mo, bakit ko ba inaaral yung dark matter? Bakit ko inaaral yung primary black holes? Right? Sa respective fields nyo, bakit ko inaaral ito? Bakit ko inaaral yan? Bakit ko inaaral itong experimental technique na to? For instance. Right? Sometimes yan. Minsan we get carried away with the very specialized things that we do na minsan nakakalimutan natin ano yung big picture.
That's true.
Kailangan balik tayo lagi, big picture.
And I think yun lang para sa episode natin ngayon.
Yes.
And hopefully may natutunan tayo today and lalong-lalo na sa cosmic microwave background.
Oo.
Tingin
yung
ko
mga
yun talaga yung
existential questions. Alam ko na kung bakit ako nandito.
Tingin ko talaga na pumupunta sa existential questions yung field ng yung field na to. Kasi pumupunta siya sa beginnings ng early universe tapos bakit tayo lahat nandito. So, very siya. Important na area ng research. So, yun lang. And see you guys sa next episode. Paalam.
Bye!